faster because the concentration's gone up. How much faster are we going? Okay, when your back's against the wall, make a table. So we have X, and I have Y, and I have rate. We played this game some. Here's the trick. If you're having trouble seeing this, the trick is have your first one through, everybody is 1 molar. And then rate is equal to K times X, let's see, X squared Y cubed. Now, if you use this little trick, your baseline is always equal to K for your rate. Okay, but see the trick. Experiment 1. It's just a way of doing this easily. Pretend that they were 1 molar. And if they were 1 molar, rate is equal to K. Now, all they're saying is we are going to double Y. Okay, if I double Y, if it was 1 molar first, and now it's going to be 2 molar, right? If you want to be a rebel, you can make these numbers anything you want, but then welcome to your calculator. I just make them 1. So if they say double it, it becomes 2. If they say triple it, it becomes 3. So then I come out here. X is still 1, but Y is now 2. Oh, yeah? 8.
Oh, 8.
8. 2
Yeah,
times
3.
2 times 2. Okay, so if I go through the math here, 8K. Anything larger than 1K, if you go through it this way, anything larger than 1K is an increase. If it's less than 1K, like 1/2 K or 3/4 K, it's a decrease in rate. But just punch in whatever they told you. And if you remember this business about these are 1s and these are 1s, okay, then just double or triple whatever they say to do. Okay, onward here. You want to take a quick 5-minute break? Do you need to stretch a little bit? We just finished up through the first unit with 3 chapters. Let's take a 5-minute, and then we'll come back and we'll work a few more. Probably work until around 12, and then we'll pick up tomorrow where we're stopping today. Get up and move around a little bit. Get blood back to your brain. Hey, how are you? Good.
I don't remember it really. How was your test? Midnight.
We don't want to think about that. Let's just skip those for the time being. And let's look at the way it's worded here. Oops, I picked up the wrong one. I should be showing the one without my answers on it. Here. Pretend you didn't see that. When I saw this problem, when I was working out your key, is I see these two that are about temperature. Okay, I don't want to deal with that. You have to know is it exothermic, is it endothermic, shift, no. Okay. The reverse reaction is favored, and then we come down here and it says the forward reaction is favored. Okay, and then it says neither. Well, the only way it'd be neither is if K is right on 1, or close to it, so I know I can trash that. And the temperatures, without even going into brainstorming, I wouldn't even think about those for the time being if I find something good. Okay, so we're really down to the reverse is favored, or the forward is bigger. So what are we going for? Reverse. Exactly. Now, sometimes the wording is a little different. It will say, if k is much, much less than 1, it lies far to the left. But that means reverse is favored. Or it may have something to say about we end up with a lot of reactants and very little product, or the reverse. So think about the different ways the language can be used here. Okay, next. 17 is just to put, now, when you look at this, you think, that is not a good balance equation because it's not the lowest coefficients that we could have used. Still, just go with it. Go with it. We have a whole section in our chapter about if we can't all come to agreement about how the equation is written, then the k's will not be the same. So if they write it like this, you take it like that, even though that's not the best form. So which is our best match? Look down through those, or if you want to be safer, write it first and then go back and look. So remember with k's, it's always products over reactants. So let's not even look at the answers yet. It may say K, it may say KC, and I just look at the equation. PCl3 to the 8th. Okay, I know that's going to be my numerator. So that throws out, in fact, that throws out all the answers with the right one. I don't even have to finish it off. I know it's going to be A. But if we want to finish it off, it would be phosphorus to the 8th, chlorine to the 12th. No, that's not good form. But just go with it. Okay, that? All right, onward. Okay. The equilibrium constant is given for one of the reactions below. Okay, this D stands for deuterium, that other isotope of hydrogen, but you don't even have to know that. Okay, we have 2HD yields H2 plus D2. And here's the K. Now they're calling it KC, because there would be explosive concentrations. Now, how did they go from here to here? Okay, this is kind of a manipulation thing, but you got to keep it straight in your mind. Manipulation with the thermo chapter with delta H's is a different animal than manipulation in this K business. This is more sophisticated, really, because here coefficients become powers. Okay, so first, when I go from here to here, what's happened to the equation? Did they flip it on us? Yes, they did. Well, if they flipped it on us, then that means right off the bat, they flip it, I got to take the inverse. Okay, now remember, this is not like the delta H stuff, where if you flip that, the sign changes. So don't get those two confused. Now, did anything else happen? We flipped it. We multiplied it by 6. So we did two things. And on these things, the worst you could do is two things to it. You can flip it and multiply it by a factor. Okay, so I got to take that. If we multiply the equation by 6, what happens to my numbers here? What will I have to do to this thing? Raise it to the 6th power. Okay, so you want to divide 1, divide it by 0.2. I either take it in, however you like it on your calculator. And then what I would do is the caret and say 6. But be sure you got your calculator so you know how to go to the 6, not 6 root, but go to the 6th power. When did we get to this? Because we multiplied. To go from here to here, we must have multiplied by 6. See, the hydrogen became 6, the deuterium became 6, this became 12. Okay, onward. Oh, what was the answer? Anybody catch that?
B.
B is in board. B is in board. Okay. Bravo. Bravo, yeah. Or whatever you can think of. Okay. at 900 Kelvin, the equilibrium constant Kp for the following is 0.345. Now that first sentence, really all I want out of it is the 0.345. Okay, at equilibrium, the partial pressure of the SO2 is 35 atmospheres. That of oxygen is 15.9 atmospheres. The partial pressure of SO3 is 1. Now, first of all, what I would do, we're talking Kp, I would just write the expression. And we know it's not going to be a real brain strain because it doesn't say anywhere initial. It just has at equilibrium. Okay, so in terms here, SO3 squared over SO2 squared times O2. Okay, well, because first of all, they're talking Kp, and then they come down here and say the pressure. That's a good point, that it would be nicer if they put, oh, I see, oh, they just left it off 1, because they're not very good integers. Okay, do you see what she's concerned about? Yeah. That doesn't have the state. Okay, but it's got to be gas. If we're doing Kp, it's got to be gas. Okay, it's just an oversight. I didn't even notice that it wasn't there. And then they come down here, though, and they tell you SO2 has this atmosphere, which implies that it's gas. Okay, now since they didn't say initial, then probably they give us everything but one of these things. And so, let's see, Kp, 0.345. And then when you're doing Kp problems, you always want to use atmospheres. And I don't think I've ever seen it as a trick that they give you torr and you have to switch it to atmospheres. So let's see. SO2 is 35. There we go. And let's see, O2 is 15.9. And we want to know SO3, so call it X. You just got yourself a little algebra problem. Okay, so you're going to take this and square it, multiply that times this, swing it over to the other side, multiply it, and move it across, and then take the square root. And we don't have to worry about units. Units, since this has no units, then we just know it's got to come out to the atmospheres. So when you punch that through, okay, D as in dog. Delta, dog. Okay, we good? All right. Dinitrogen hydroxide partially decomposes according to the following equilibrium. N2O4 goes to 2NO2. Okay, a 1 liter flask is charged with, that's kind of strange word, it just means it's charged with putting it into 3.00 times 10 to the minus 2 moles of N2O4. At equilibrium, 2.36 times 10 to the minus 2 moles of N2O4. Okay, we're talking brain strain on this one because this here is kind of code, so that means initial. So let's see what we have to do. So the first thing I would do, stalling for time, that I would write it, and we're talking Kc. Now notice in this problem they're using kind of an obsolete term KEQ, but K, KEQ, Kc, all that stuff means the same thing. So I'm just going to call it Kc. We will have NO2 squared over N2O4. Okay, that's step one. Whenever you have an equilibrium problem you think is going to be challenging, you know you need that. So take the time and write that out. Okay, then they do mention a 1 liter flask. But you know what? We're just going to laugh at them because the number of moles divided by 1, so they've really given us molarity. But do you see how this could be more challenging? They could say in a 5 liter flask. That means every number of moles they give you for this gas has got to be divided by the 5 liters. But here they're just saying it's 1 liter. I usually take the time and sketch it, but then I see, it's just 1, no sweat. Okay, then, ice table. So we have N2O4, and we have NO2. Okay, so what are they telling us here? Why don't I just do this? Let me move into regular notation. Okay, initially we have 0.0300 moles per liter because it's a 1 liter flask. So that's the concentration initially of this. What do we assume this to be? 0. Okay, now, can we have an X in here? No, because we don't have K, do we? So that means we've got to do brain strain and figure all this out. Okay, the other thing they tell us, though, in the next sentence is that we have an equilibrium. And I'm just moving this into regular notation. Just my preference. If you don't like it, don't do it. That's what we have in equilibrium. Now, I would also when you're doing a difficult, challenging equilibrium problem, step 1, you want to write this. Step 2, think initial is in there somewhere. You need your ice table. Let's call that step 2. Step 3, I think it's very, very useful to use these verbs here. Anything on this side we're making, anything on that side we're using. Okay, so what they're telling us is, the first of the day, I started with this much, and at the end of the day, I ended up with this much. Okay, but that doesn't tell us right now how much we used. It just said you started with so much, you ended with so much. Okay, remember the coffee business? You had so much money in your pocket, you stopped at Starbucks on the way home, you paid for your cup of coffee, you put the change in your pocket. Okay, when you get home, you have to count what's left. So you know what you started with, a $5 bill, and at the end, you know how much you got home with. How much did you use or spend? You have to subtract. And so what this is telling us, we started with this, we ended up with this. So how are we going to know how much we used? Subtract the 2. And when I subtract the 2, what do we get? 0.0064. So up here, 0.0064 was used. Okay, we're good? That's really the make or break thing. Okay, now, here's where the coefficients come in. If you want, you put here that is the change. Because they gave us this, they gave us that, and we had to come up with that for ourselves. Okay, now, every time I use one of these, I make 2 of those, don't I? Okay, so how do I get how much we make? It'll be 2 times what we used. Okay, so what is that? We've got 0.128, is that right? I'm getting brain dead. Okay, so we made that much, so that's how much we end up with. Okay, now all we have to do, see, you've done the hard work here. After that, just be careful of the math. Okay, so we have NO2, 0.0128, and we have to square it. And I always give this speech. Yeah, we dealt with the two different times, but for two different reasons. This we have to square no matter what we stick inside of here. How did we get this? Our reasoning. Every time we use one, we make twice as many. So yeah, we dealt with the two. And then we have 0.0236. All right, and our answer is, does anybody have that question? D, did you say? What's that? Let me see what I got. I'm getting D. 6.94 times 6 minus 30. Okay, it must just be your math. If you've set it up exactly like that, it's probably a math. Did you find it?
No, he was asking me a free card.
Oh, okay.
Making fun of me.
He's making fun of you?
Yeah, he asked me about gradients.
Okay, we good with this? I mean, calculator's good. Work? Okay. All right, let's move on.
Wait, what was the problem though? To decide if the question was written wrong or?
No, Jerry can't punch his calculator. I think is what we
I guess I
decided.
can't either.
You can't either? Well, let me grab one. Lizette, you really punched it through, right?
It's right here.
Okay, are we down to here? Okay. Is everybody, Jerry, did you get to hear it in agreement with us? And Michelle, did you get to hear it in agreement with us? Okay. Did I miss an extra zero here?
I did.
You did.
So,
I wrote the chair, but you should have done.
Okay, so you wrote something down wrong.
yes.
Okay, Michelle.
Okay.
We saw one wrong.
I wrote a deal wrong.
You wrote it down. Okay, great. Okay, let's move on. Let's do. I'm so conditioned I look over there for the clock. Okay. Now, what is the conjugate acid? All right. First of all, you see that word conjugate? You know we're talking about Bronsted. We just moved into the next chapter. Okay. Now, HCO3 minus. They are asking you for the conjugate acid. That must mean this is acting as a base. Okay, in Lowry-Bronsted talk, an acid is a what? Two-word answer. Proton donor, or three-word answer, hydrogen ion donor. And a Lowry-Bronsted base is a proton acceptor or a hydrogen ion acceptor. Okay, so what is the conjugate acid of this? That means it has been acting as a base, so it's accepted one, so give it one and adjust the charge. So what's our answer? E, as in easy. We good? Okay, that means this is a base. E. If it's asking for the conjugate acid, then this must be the base. Okay, so it's saying HCO3 minus. When it's saying, what's the other one, then it's got to be the opposite. Okay, so if it's a conjugate, if it's the base, that means it's accepted a hydrogen ion. So I'm going to give it one. And when I give it one, hydrogen ion is a +1, so the charge goes to that. Okay, now, what if you have the same question? It says, what is the conjugate base of this? So that means this must be acting as an acid, right? Okay, so if it's an acid, it's a donor. So take one away. What's my charge now? 2 minus. concentration of hydroxide ions in pure water at 30 degrees Celsius if Kw at this temperature is this. Now, you all were supposed to memorize Kw, and you memorized it 1.0 times 10 to the minus 14. But that's standard. This says you're at 30. We will not work this problem any differently. It's just that we have slightly different Kw to work with. Okay, we are in pure water. Pure water. Here's our equation for the auto ionization of water. You get a hydrogen ion and a hydroxide. Or if you want to be more exact, you could say it's two waters and you get the hydronium and the hydroxide, but this is the shorthand version. Okay, Kw is equal to this. Why do I leave the water out? It's a pure liquid. We always leave pure liquids out of these. So all I have to do, every time we make a hydrogen ion, we make a hydroxide in pure water. So could we just call that x times x, or x squared? And we have 1.47 times 10 to the minus 14. Okay, so if it's pure water, this is understood. We'll let that be x, and we know we can have an x because we know the k. And so we're going to take the square root of both sides, and that's going to give us hydroxide. Hydrogen ion. And when you do that, what did you get? A. Okay. Everybody good? No. Jared, what's the problem? Oh. Okay, if you wanted to go through, because Kw, the way it's written, no sweat there, right? And you know why we leave the water out. Okay, at time 0, I've got none of that, I've got none of that. Now, on this table, at this point in time, I would say, could I have an x? Yeah, I